For centuries, the natural world seemed to operate in silos. Electricity was the spark that flowed through wires, while magnetism was the property of lodestones and compasses. They were treated as distinct, unrelated forces. That changed in 1820, when Danish physicist Hans Christian Ørsted noticed a connection during a routine lecture. While demonstrating an electric circuit, he saw a nearby compass needle twitch. Every time the current flowed, the needle, which should only respond to a magnet, moved as if a new magnetic force were pushing it. This accidental observation proved that electricity and magnetism were not separate. The current in the wire was actually producing a magnetic effect in the space around it. This link became the basis for medical tools like the MRI. These scanners detect the tiny magnetic fields produced by ion currents in our own nerves, turning the physics of Ørsted's wire into a window into the human body. To understand how this works, consider a simple straight copper wire. When we connect it to a battery, electrons begin to flow through the metal, creating a current. This motion generates a magnetic field shaped as concentric circles expanding outward. Using the right-hand thumb rule, if your thumb points with the current, your fingers wrap in the magnetic field's direction. If we increase the current, the field grows denser in direct proportion. Because the strength of the field responds directly to the amount of current we provide, we can adjust the power of this invisible force simply by turning a dial. Bending a straight wire into a circular loop forces its magnetic lines to converge. Stacking many loops into a cylinder creates a solenoid. Within this coil, the fields combine into parallel straight lines, making it behave exactly like a permanent bar magnet. If we place a piece of soft iron inside this coil, the solenoid's field magnetizes the iron, creating an electromagnet. This gives us a magnet that is only active when electricity is flowing. By reshaping the wire, we take a weak effect and concentrate it into a predictable force, powerful enough to drive heavy industrial machinery. In the years following Ørsted's discovery, André-Marie Ampère realized that if a current-carrying wire could move a magnet, then a magnet must also exert a force on the wire. Suspended between a horseshoe magnet, an aluminum rod is physically displaced when current flows through it. We map this push using Fleming's left-hand rule. The first finger represents the field, the second the current, and the thumb points to the resulting direction of motion. This push is the physical mechanism that converts electricity into kinetic energy. It is the basis for the electric motor, using magnetic fields to create constant, reliable motion. To use these powerful electromagnetic forces in our homes, we rely on standardized systems to route current safely. In a typical domestic circuit, a live wire brings power in, and a neutral wire completes the loop. To prevent shocks, a third earth wire connects the metallic bodies of appliances directly to the ground, providing a safe path for any leaking current. However, if insulation fails and the live and neutral wires touch, the current spikes abruptly. This short-circuiting creates a surge of energy that can damage the system. This is where we rely on the thermal effects of electricity. The sudden surge causes intense joule heating, which melts the fuse and breaks the circuit before the high current can cause a fire. By decoding a twitching compass needle in 1820, humanity transitioned from witnessing a curiosity to building a global infrastructure. We learned to use electricity not only to generate light and heat, but to create the motion and fields that power the modern world.